A ripple in space-time arrived from deep within the fabric of the universe. It was subtle, almost imperceptible, but it carried a story that would shake the foundations of astrophysics. What LIGO detected wasn't just another black hole merger, it was something long thought to be impossible. This was a forbidden black hole. A cosmic collision so massive, so violent, and so unexpected, it defied everything scientists believed about how black holes are born and how they die. The waves that reached Earth weren't just vibrations, they were a message. A whisper from the darkest parts of space, announcing the fusion of two giants that shouldn't have existed in the first place. Gravitational waves, like echoes of ancient thunder, revealed an astronomical event that science had no room for. A merger that didn't just challenge existing models, it shattered them. What made this black hole merger so mysterious wasn't just its size or strength, but the fact that it broke the rules. It existed in a range of mass that was considered forbidden by current theories. Scientists were stunned, the astrophysics community reeled, and questions spread faster than answers. What could create such a black hole? How did it form? And what else might be hiding in the shadows of space? In this video, we're diving deep into the forbidden. You're about to witness the most massive black hole merger ever recorded, and learn why its existence is rewriting the rulebook of the universe. Breaking news from the edge of reality. On a quiet day in May 2019, a signal arrived at Earth that had taken billions of years to travel here. Detected by the Laser Interferometer Gravitational Wave Observatory, known as LIGO, and confirmed by the Virgo collaboration, this signal marked one of the most significant gravitational wave discoveries ever made. Scientists named the event GW190521, and it became instantly historic. What LIGO detected was no ordinary cosmic tremor, it was the unmistakable signature of two colossal black holes colliding. One black hole was around 85 times the mass of our Sun. The other weighed in at about 66 solar masses. These were already among the most massive stellar black holes ever observed, and when they merged, they created an even larger giant, clocking in at a staggering 142 solar masses. The gravitational waves emitted during this collision radiated more energy in a fraction of a second than all the stars in the observable universe combined could emit in the same time. This wasn't just another black hole merger. It was the most massive black hole merger ever recorded by gravitational wave detectors. What made this discovery even more extraordinary was that one of the merging black holes fell within a so-called mass gap, a range of black hole masses that theoretical models say shouldn't exist due to the way massive stars die. The event originated from over 17 billion light-years away, meaning it happened when the universe was still young. And yet, the signal it sent was powerful enough to ring across space and time. Researchers at LIGO and Virgo immediately realized this was unlike anything they had seen before. In their words, it was a detection that defies conventional understanding. What LIGO detected wasn't just a black hole, it was a challenge. A puzzle piece that doesn't fit into the existing picture. And as scientists examined the data, the mystery only deepened. What are gravitational waves? Imagine space not as a void, but as a fabric, fluid, flexible, and alive with motion. When massive objects like black holes move, they disturb this fabric, creating ripples that travel across the universe. These ripples are called gravitational waves. First predicted by Albert Einstein over a century ago as part of his general theory of relativity, gravitational waves were once thought to be too faint to ever detect. But then came LIGO. Gravitational waves explained simply are waves of stretched and compressed space, generated by some of the most violent and energetic events in the cosmos. LIGO, short for the Laser Interferometer Gravitational Wave Observatory, is the instrument that changed everything. Using two enormous L-shaped detectors with laser beams traveling down vacuum-sealed arms kilometers long, LIGO can detect shifts in space smaller than a fraction of the width of a proton. When a gravitational wave passes through Earth, it causes these arms to slightly lengthen or shorten, and LIGO records the signal. Since its first detection in 2015, LIGO has opened an entirely new window into the universe. One of its early triumphs was recording the collision of two neutron stars, which confirmed how heavy elements like gold are created. Another was the 2017 detection of a black hole merger that provided direct proof that gravitational waves exist, matching Einstein's long-standing prediction with stunning precision. Gravitational wave astronomy matters because it allows us to observe cosmic events we could never see with light alone. These waves carry information about dark corners of the universe, collisions, explosions, and mysterious phenomena hidden behind clouds of dust or buried in deep time. With every wave detected, we're not just hearing the echoes of ancient violence. We're rewriting physics, revealing secrets, and witnessing the universe in a brand new way. Why this merger is forbidden? There are rules in astrophysics, limits that define what kinds of black holes can exist, and how they come to be. Stellar mass black holes, which form from collapsing stars, typically weigh less than about 50 times the mass of our Sun. At the other end of the spectrum are supermassive black holes, millions or even billions of times more massive, usually found at the centers of galaxies. In between lies a strange desert, a mysterious range of masses between about 50 and 120 solar masses, where black holes are not supposed to exist. This is known as the upper mass gap. According to current models of stellar evolution, when a star gets too massive, it doesn't form a black hole at all. Instead, it undergoes something called pair instability supernova, an explosive process that tears the star apart completely, leaving behind nothing. That means a black hole with a mass between 50 and 120 suns shouldn't be there. Yet that's exactly what LIGO detected. One of the merging black holes in the GW190521 event measured around 85 solar masses. That puts it right in the middle of the forbidden zone. How did it get there? That question has sparked intense debate and challenged everything we thought we knew about how black holes form. Some theories suggest hierarchical mergers, black holes that were themselves formed from earlier black hole collisions. Over time, these could grow large enough to fall into the mass gap. Others propose direct collapse, where massive gas clouds collapse directly into a black hole without forming a star first. And then there's the most radical idea: primordial black holes, born not from stars but from the high-energy chaos of the early universe. Whichever explanation proves correct, one thing is clear: the forbidden black hole merger LIGO detected has shattered the confidence scientists once had in their models. The black hole mass gap may not be a gap at all. It might be a clue. A sign that the universe has more to show us than we ever imagined. How big was this collision? To understand just how massive this collision was, you need to stretch your imagination far beyond the scale of anything familiar. This wasn't a simple fusion of two stars or a typical black hole encounter. The LIGO event GW190521 revealed the most massive black hole merger ever detected by gravitational wave observatories. The two black holes that collided were enormous on their own, but their final union created something that stood on the edge between stellar and intermediate mass, a realm rarely seen, and even more rarely understood. The resulting black hole, clocking in at 142 times the mass of our Sun, marked the first direct evidence of an intermediate mass black hole ever detected. To put it in perspective, the energy released in that single collision was equivalent to roughly 8 solar masses converted directly into gravitational waves. In just 1/10 of a second, more energy was emitted than all the stars in the observable universe combined could release in the same fraction of time. It was a blast of cosmic violence that bent the very shape of spacetime. Imagine two invisible giants hurtling toward each other, spiraling faster and faster in a final death dance. As they approach, the combined gravity twists space like a whirlpool. The frequency of the gravitational waves rises rapidly, producing a burst of energy so strong it vibrates across the cosmos. The wave that reached Earth was short but unmistakable, a chirp lasting less than a second, carrying the fingerprint of the most massive black hole merger ever observed. This wasn't just a large black hole. It was an astronomical anomaly. A black hole-size comparison with previous events puts this one at the top of the list. GW190521 didn't just set a new record, it opened the door to an entirely new class of black holes that we didn't even know were out there. Scientific reaction: shock, doubt, and debate. When the data from GW190521 first appeared on LIGO's instruments, the initial reaction from scientists was disbelief. It wasn't just surprising, it was unsettling. The masses were too large, the signal too brief, and the implications too profound. Many researchers assumed it was a data glitch or perhaps a miscalculation. But after rigorous analysis and confirmation from Virgo, the reality became undeniable. The scientific community was now staring at something that simply shouldn't exist. The idea of a forbidden black hole merger had long been discussed as a theoretical edge case, but no one expected it to show up this soon, this clearly, or with this level of force. Theories of stellar evolution were built on well-modeled mass thresholds, and this event broke through them like they were suggestions, not rules. Scientists who had spent decades developing models for black hole formation were suddenly forced to reconsider everything they thought they knew. Some saw the event as validation of a concept called hierarchical mergers. In this scenario, smaller black holes form first, then collide again and again, eventually growing into giants that land squarely in the mass gap. Others leaned toward a different idea: direct collapse. According to this theory, massive clouds of gas in the early universe can collapse under their own gravity without ever forming stars, bypassing traditional limits. Then there were the more speculative possibilities, including the existence of primordial black holes. These would be relics from the earliest moments after the Big Bang, formed from the high-density fluctuations in the young cosmos. Not everyone was convinced. Some astrophysicists urged caution, pointing out that the margin for error in mass estimation through gravitational wave data can be wide. Others questioned whether we were even interpreting the signal correctly. Perhaps it wasn't a black hole merger at all, but something more exotic, a boson star or a new type of compact object not yet catalogued by science. But despite the skepticism, the excitement was undeniable. The LIGO scientific community reaction ranged from cautious optimism to open awe. This event sparked a flood of new papers, new simulations, and a wave of renewed curiosity. Theories will clash, models will adapt, and some explanations may fall away entirely. What remains is the indisputable fact that something extraordinary happened. And for a scientific field that thrives on discovery, few things are more thrilling than being proven wrong by the universe itself. Case studies of past, impossible, discoveries. The universe has a way of humbling even the most confident theories. While the GW190521 event made headlines for being the most massive black hole merger ever detected, it wasn't the first time LIGO spotted something that challenged expectations. Over the past several years, the observatory has compiled a growing catalogue of black hole mergers that have slowly chipped away at old assumptions. Again and again, gravitational wave signals have revealed black holes with unexpected masses, spins, or behaviors. One of the most memorable events before this one was, in fact, GW190521 itself. At the time of its discovery, it was already considered a record breaker. The masses involved were thought to be near the limits of stellar formation. Even then, the notion that a black hole could exist in the mass gap was controversial. That event pushed scientists to begin revising physics models and questioning the processes that govern stellar collapse and black hole formation. As more strange black hole mergers began to appear in the data, patterns emerged. Some events showed black holes spinning far faster than predicted. Others involved collisions between black holes that shouldn't have formed from traditional stars. These findings forced astrophysicists to expand their theoretical frameworks. Equations were rewritten. Simulations were recalibrated. What once seemed like anomalies were now forming a trend. Instead of dismissing these cases as outliers, scientists began to see them as signposts, evidence that our understanding of black hole evolution was incomplete. The gravitational wave discoveries made by LIGO weren't just adding new black holes to a catalogue. They were reshaping the very structure of how we model the cosmos. Each wave carried not just information, but a challenge. A dare from the universe to keep asking, keep adjusting, and never assume that the rules are final. What this tells us about the universe: the forbidden black hole merger uncovered by LIGO isn't just a singular event, it's a profound clue about how the universe works, and how little we truly know about it. The discovery raises important questions about the origin of massive black holes. If these objects can form in defiance of known stellar processes, then we must consider new mechanisms of star formation and death. Perhaps the life cycle of stars is more chaotic and unpredictable than we thought. This collision also opens a window into the behavior of the early universe. When we detect a gravitational wave from billions of light years away, we're not just witnessing an event, we're traveling back in time. The conditions that produced such massive black holes may have been more common in the young universe. Dense gas clouds, primitive galaxies, and high-energy environments may have allowed for the direct collapse of matter into black holes without passing through a stellar phase. These early events could be the missing links in understanding how supermassive black holes form so rapidly in the centers of young galaxies. But with every answer comes more uncertainty. Could dark matter play a role in these unexplained mergers? Are we glimpsing hints of a multiverse or the influence of hidden dimensions? Or are we simply facing the limits of our current instruments and imagination? Classical astrophysics, with all its elegant equations and stellar models, may no longer be enough to explain what we're observing. The forbidden black hole merger isn't just about size or rarity. It's about possibility. It tells us that the universe is still writing its story in ways we don't yet understand. And we, standing on our small planet with detectors tuned to the cosmos, are only beginning to hear the full story. What's next? LIGO's future discoveries. If LIGO's past has taught us anything, it's that the cosmos holds surprises beyond imagination. And the future of gravitational wave astronomy is about to get even more exciting. LIGO and its European counterpart, Virgo, are undergoing upgrades that will sharpen their sensitivity and expand the range of detectable events. Soon, Kagra in Japan will join them in full force, giving us a global network of eyes and ears on the universe. But even more ambitious observatories are on the horizon. The Einstein telescope and the Cosmic Explorer are next-generation gravitational wave detectors designed to probe deeper into space and further back in time than ever before. These instruments will allow scientists to detect fainter signals, uncover smaller black holes, and perhaps even pick up whispers of entirely new physics. Researchers are already dreaming of what could come next. Could we finally detect a white hole, an object theorized to expel matter rather than consume it? Might we uncover the faint signature of a wormhole, or evidence of a hidden fifth force? Each new detection opens the possibility of rewriting the rules once more. LIGO's future discoveries may not just refine our models, they could redefine reality itself. A universe that breaks its own rules. The detection of a forbidden black hole merger is more than just a scientific milestone. It's a reminder that even in a universe governed by laws and equations, surprises are not only possible, they are inevitable. LIGO's discovery didn't just measure mass or energy. It measured the gap between what we know and what is still waiting to be discovered. This black hole defied the limits of stellar evolution, crashed through the mass gap, and sent gravitational waves that traveled across space and time to shake our understanding of the cosmos. It challenged astrophysics, tested our models, and dared us to think bigger. So what else is out there? What other mysteries lie hidden in the dark, silent corners of the universe, just waiting for the right instrument, the right question, or the right moment to reveal themselves? If you're fascinated by space mysteries like this one, make sure to subscribe. Because the story of the universe is still unfolding. And the next chapter might be stranger than anything we've imagined. This is LIGO's latest discovery. This is the forbidden black hole. And this is just the beginning.